Okay, so for this problem, we have a rectangular plate that's drawn out here in black, and it's 250 millimeters by 300 millimeters, and it gets deformed into a trapezoid. So that's what we see in red. The bottom of the plate stays the same, and then basically if we want to imagine there are lines that are horizontal in this plate, after it gets deformed, those lines continue to be horizontal, and they have the same length, okay? So just for, there's our coordinate system. So you can see that when the plate gets deformed, the top is 2 millimeters below where it was, and then the side is pushed out to 3 millimeters past its original position, okay? So in this case, we've got both normal strain and shear strain. So let's talk about the normal strain first. We want to determine the average normal strain along the side AB, so along this left-hand side here. And you can see that the corner B gets pushed down to B prime. So that means that it's shortened a little bit, okay? So we can think of this as a triangle. We want to compare the length of AB and AB prime, okay? The vertical length. So the vertical side is AD of our new triangle, and we need to figure out the side of that. So that's going to be 250 millimeters minus 2, because that's how much shorter it is, and that gives us a length of 248 millimeters, okay? And then we need to figure out the distance between D and B prime, so that we can basically use Pythagorean theorem to get the length of AB prime, okay? So dB is basically that offset that we see over here, so that's going to be 3 millimeters, okay? So we're going to find the total length of AB prime by taking 248 millimeters and squaring that, plus 3 millimeters, squaring that, square rooting the whole thing, and that tells us that the length of AB prime is equal to 248.018 millimeters, okay? So we want to find the average normal strain, and again, this is the difference between the original length and the final length divided by the original length, so that's going to be delta S prime minus delta S over delta S, okay? In our case, we can write this as AB prime minus AB over AB. That's going to be 248.018 millimeters minus 250 millimeters, and then dividing by 250 millimeters. Okay, so that means our average normal strain will be equal to minus 7.93 times 10 to the minus 3 millimeter per millimeter. Okay. Why do we have a negative there? That basically means that our total length is shorter than the original length, so then that means we have contraction. Okay. For the second part of this, we want to find the shear strain on the plate relative to the x and y axes. So basically, shear strain is the change in angle that occurs between two lines that were originally perpendicular. So in our case, what we've got is we've got A, B, and C, and this theta here is originally perpendicular, and it's going to get changed to, I gotta draw my angle better, A, B prime up here, and C, and then we're going to call this new angle theta prime, okay? So mathematically, we write this as gamma, yet another gamma, right? N and T are the axes, okay, equal to pi over 2, that's the original angle, theta, because originally it's perpendicular, minus the limit of theta prime as B goes to, well, I think I might have these swapped. let me, as, sorry, as B, sorry, I wrote my axes out opposite here. B, A goes to B along N, okay? And then as C goes to B along T, okay? So basically as we're going along these sides, how much has this angle shifted, okay? If theta prime is less than pi over 2, then our shear strain is positive. If it's greater than pi over 2, then it's negative. Okay? So for our problem, we're going to think about this. We've got our theta prime, right? And we decided that this side was 3 and this side was the 248.018. Okay. Oh, yeah, no, that's right. Okay. So I'm basically going to take the tangent of theta prime with the opposite over the adjacent. So the opposite is going to be this side and the adjacent will be that side. Okay, so that's going to give us that theta prime is equal to the inverse tangent of, well, we're going to have the 248.018 over 3, which gives us a theta prime of 1.5587 radians, and we want to be working in radians here. Okay, so our shear strain, not stress. Our shear strain will be equal to, on the xy axis, pi over 2 minus 1.5587 radians, which ends up being equal to 0.0121 radians, or if you like thinking in degrees, this is 0.693 degrees.